Regression Kriging, Generalized Additive Model and Generalized Least Squares.
This is the fourth geostatistic course about Kriging and co-Kriging interpolation and mapping. With this course, you are going to learn the different types of Kriging interpolation, like ordinary Kriging, universal Kriging, regression Kriging, Kriging with external drift, and also ordinary co-Kriging. We already saw the ordinary Kriging and the universal Kriging, and now we are working on the regression Kriging. For this third lesson about regression Kriging, we have different parts. The part number 0, it was the introduction. The part number 1, it was about how to create a grid using a shapefile with R and QGIS. The part number 2, it was about ordinary least squares. The part number 3, it was about generalized least squares. The part number 4, it was about overfitting, the ultimate analysis. And today we are going to be working on the part number 5. Today in this lesson we are going to be focused on the creation of two models based on regression Kriging. First, we are going to be working on generalized additive models, plus the ordinary Kriging associated with the residuals of this trend surface. Then we are going to plus the deterministic model plus the stochastic model in order to create a regression Kriging. Later we are going to work with the generalized least squares on a regression Kriging. Then we are going to use the second order trend surface from the generalized least squares plus the ordinary Kriging created with the residual values of this deterministic model. Hey, remember, if you want to have full access to all the content, just go to the GAM-RK community website at gscourse.online. Then go to courses, get enrolled at the 4th geostatistic course, and then you are going to be ready to start learning. Here, as you can see, we have already several lessons added related to this course. The lesson number 0 is the introduction. The lesson number 1 is about ordinary Kriging. You have here more than 2 hours 30 minutes of content. The lesson number 2 is about universal Kriging with almost 4 hours 30 minutes of content. And now we are working on the third lesson. This lesson is about regression Kriging, and as you can see we have several parts. The part for today is the regression Kriging associated with two types of deterministic models, the generalized additive model and the generalized least squares. Remember that if you don't want to get enrolled at the GAM-RK community website, you can follow us in YouTube. Here you can have access to all the content with some restrictions, but if you are interested in this kind of topic, you can follow the lessons with YouTube. Before to start with today's lessons, let's go to make a very short summary about the things that we are going to talk today. First, we are going to be working with the Volcans Aquifer dataset. Remember that this dataset is based on the groundwater elevation at the state of New Mexico and Texas. At the beginning, we are going to create two different types of scatter plot to see the trend of our data. Later, we are going to create a 3D scatter plot where we are going to see the spatial distribution of our data that is going to make easy to identify the trend surface in our data set. Later, we are going to be working with generalized additive models, and we are going to create two different models. The first one is going to be more complex with 30 nuts, and the second one is going to be a little bit more simple with 10 nuts. For both of these models, we are going to make a general analysis in order to know if the models are good or are not good. Then we are going to use different type of graphs that we can use in order to make a good diagnostic, in addition with other quantitative tools that we can use in R. Later, we are going to analyze the spatial structure of the residuals associated for each of these models. Then we are going to create the trend surface of these two models. And we are going to see two different types of visualization, this one and this one. And for the second one, we are not only going to see the trend surface, but also we are going to see the map associated with the standard error for each of these models. Then what we are going to do is to take this model over here and we are going to export to QGIS. And that's the map that you can see over here. And later we are going to create a 3D interpretation of the trend surface integrated on our dataset. You are going to see that in QGIS we have a very powerful tool that we don't have in R that is going to help us a lot in order to have a 3D visualization of our model with the dataset. This tool is awesome, okay? And later we are going to take the residuals from each of these models and we are going to do the Kriging interpolation in R. And then we are going to export the Kriging to QGIS, as you can see over here. And the next step is going to be the summation of the trend surface plus the Kriging, the ordinary Kriging, in order to create the regression Kriging. And the result is these two maps. Remember that this one is for 10K and this one is for a 30K. And also we are going to be analyzing the 3D model associated with this regression Kriging, where we are going to see that the result that we get is not really good, and we are going to be analyzing the reason of that. Then the last thing that we are going to do is to work with the residuals of the generalized least squares. We are going to analyze the structure and we are going to create the ordinary Kriging of those residuals in R. Then we are going to export the ordinary Kriging to QGIS, and we are going to take the ordinary Kriging from the residuals of the generalized least squares plus the second order trend surface of the generalized least squares, and we are going to create the regression Kriging. At the end, we are going to see another tool that is going to help us a lot in order to compare these two different models, okay? Well, that's it for the summary, and let's go to start with the lesson. Today we are going to be working with the Volcamp Aquifer dataset. Remember that if you want to know how I get this dataset, my recommendation is to watch the second lesson of the 4th geostatistics course about universal Kriging, where we introduce the Volcamp Aquifer dataset. In this dataset, what we have is just the UTM coordinates and also the groundwater elevation in meters above of the sea level. Then what we have for each sample location is the X and Y coordinate and also the zeta coordinate. And with the zeta coordinate, what we have is the groundwater elevation. But this zeta coordinate could be any other variable, could be the pH of the soil, could be the electroconductivity of the soil, could be the concentration of a metal in the soil. As you can see, it could be any other variable. But in this case, the zeta coordinate is just the groundwater elevation measured inside of a piezometer. The goal of this exercise is to predict the groundwater elevation in those locations where I don't have any sample using the regression Kriging. Remember that with regression Kriging, we have the variable of interest located at the space that is equal to a deterministic model plus an stochastic model. In a previous lesson, we was working already on the deterministic model associated with the ordinary least squares, where we predict the first order trend surface and the second order trend surface associated with the Volcamp Aquifer dataset. And that's the information that we can see in this map over here. This one is the first order trend surface, and this one is the second order trend surface, and both were calculated using the ordinary least squares. Later, we was working on the generalized least squares, and we calculated the second order trend surface. And the result, it was this map over here. And as you can see, there are some differences between the second order trend surface from the generalized least squares and the second order trend surface from the ordinary least squares. And today what we are going to do is create the trend surface associated with the generalized additive model. Remember that when we was working with linear models associated with the ordinary least squares, what we did is fit a polynomial surface of first and second order in the data. For the linear models associated with the generalized least squares, what we did is fit a surface of second order in the data, taking in consideration the spatial autocorrelation of the residuals. Now, for the generalized additive models, what we are going to do is divide the data set in different sections. As we explained at the previous lesson, the limit of each section is a NAT. For example, if we have 10 NATs, we are going to have 9 different sections. And for each of these sections, what we are going to do is fit a surface that is unexplained. Then we are going to have, for example, if the division is 9 sections, we are going to have 9 different splines fitted in each of these sections. These splines are going to be the thin plate splines that are the ones that appears by default when using the package MGCV for generalized additive models. Then if we want to predict the groundwater elevation, that is going to be the variable of interest, in those spatial locations where we don't have samples, we need a deterministic model that is the trend surface, and this deterministic model in this case is going to be the GAM plus an stochastic model, and the stochastic model is going to be the ordinary Kriging, and we are going to apply the ordinary Kriging to the residuals that we get from the GAM, and that's what we are going to do now with R. Then first let's go to create a new project. New directory, new project. We are going to select a folder. I'm going to save in this folder over here, open, and the name of this project is going to be GAM dash, and it's going to be 3.4.3.5, and then create the project. And the next step is to open the windows for the scripts. In this case, we have to go here, our scripts, and now we can paste here what I did already. Now we're going to start from the beginning, and in this case what we are going to do is the generalized additive model, GAM, for the groundwater elevation. In this case, we are interested to analyze the groundwater flow direction, okay? Then we can run the first libraries, that is going to be the ggplot, the SP, and the gstats. Then the next step is to load the dataset. The dataset is located in this folder, dataset, and it's this one. Then I'm going to copy the link, copy, and I'm going to paste over here because this link is a different one. Then paste over here, change the direction of the dash bar, is this one, and the rest is okay. Then we can run this one now. The new data set is located over here, and I call this one as the letter A. We can open here, and it's the same as we saw with QGIS, right? The X coordinate, the Y coordinate, and the groundwater elevation for a total of 85 samples or 85 measurements of the groundwater elevation at the piezometers. Then the next step is to create a backup. In this case, it's going to be A2. And now we are going to plot the trend on the X coordinate. It's going to be a scatter plot where we are going to see the groundwater elevation against the X coordinate. To do that one, we are going to use the ggplot. And if we select this section of the code, we can run to see the graph. Then we can go here to the graph, plots here, to be clear where is the trend of this data set, okay? Here we have the x coordinate, here we have the groundwater elevation, and here we added the regression line. And as you can see, there is a very clear trend surface in this direction. Now we are going to do the same, but for the y coordinate. Now also we can select this portion and run this one to see what is the relation between the groundwater elevation and the y coordinate. And again, we can see clear that there is a trend. In these two cases, we was working in 2 dimensions with the x and the groundwater elevation, and in the other case with the y and the groundwater elevation. And in order to fit a model on our data, that is the regression line, we was using a linear model that is nothing related with the generalized additive models. We was using just the linear models to see the trend of our data. Now we are going to do the interpretation of 3 dimensions of this data set. Then let's go to run this script. Let's go to load this library. Now we're going to attach the data set, and now we can do the plot in 3D. We can open this one, and in this graph what we have is the x coordinate in this axis, the y coordinate in this axis, and the groundwater elevation in this axis over here. Then we can rotate this graph on the space in order to see the trend surface of our data. As you can see, this trend surface is follow this direction. Now we can move to the next script. In this case, now we are going to work with the Generalized Additive Models, GAM, okay? In order to work with these models, we are going to load this package over here, the MGCV. Then we can run this script, and now we can work on our first model. The first model is going to be this one, and the object is going to be called as a GAM model. Then we are going to use this script, where we are saying that the groundwater elevation is depending on a smooth function for the x and the y coordinate, and the data set that we are going to use is A, is this one, and the method is going to be the restricted maximum likelihood. For this first model, we are not going to assign any nuts, just we are going to leave the value that appears by default. Remember that when we are working with generalized additive models, the data set is divided in sections, and each section is limited by nuts. Then, for example, if we have 10 nuts, we are going to divide the data set in 9 different sections, and for each of these sections, we are going to fit and explain. Then, as bigger is the number of nuts, more complex is going to be the model. Then we are ready to run this model. And now we can see the summary related with this model. What kind of information we have here? Well, first of all, it's saying that the family is the Gaussian for normal distribution. The link function is the identity. The formula that we are using is this one, where the groundwater is depending on a smooth function of x and y. Then here we have some parameters, and the intersect is significative. Then we have the effective degrees of freedom associated with this function, and also in this case they are significative. And at the end, what we have is how much the variance can explain this model, and in this case is 95.6%. That is a lot, right? Because the maximum is 100, and if we have 95.6, we are very close to 100. Here we have the number of samples, and here we have the method that we are using. With the next script, we are going to see the summary of the residuals associated with this model. Then we have this model, right, that we call GAM model. And then we are going to extract the residual values from this model. Remember that the residual values are the values of the observation values less the predicted values. The predicted values, it is the model, right? Then this difference is going to provide us the residual values. Now we are going to see a summary of that values. Then is this one over here. As we can see, we have the mean value, we have the median, we have the first quantile, the third quantile, the minimum value, and the maximum value. As you can see, all these values are pretty symmetric, and that one is good in order to have a normal distribution on the residuals. Now we are going to see the histogram of these residuals. And as I said previously, this histogram is showing a pretty normal distribution of our data. Then we can close this one, and also there is no outliers, okay? Now we can visualize the model in 3 dimensions, and we can play with this angle over here to have different views. Then first we can run this one. Here we have the y coordinate, the x coordinate, and the groundwater elevation. In this case, what we are saying is the predicted model associated with the generalized additive models. And all the values that are contained in this plane are the predicted values. In this case, we cannot see the observed values or the residual values. What we have is just the predicted values on this surface. Remember that the predicted values are also called as a fitted values, okay? Then now we can run the next script. With this script, we can verify if our model is good or is not good. The first thing that we have to cover is this assumption. And this assumption is saying that if we have a low p-value, maybe we are going to have a model that is not valid. When we are going to have a low p-value, when the value over here is indicating with an asterisk. In this case, the value is good because we don't have any asterisk. But if this value is low, it's because we have to increase the number of nuts. We have to make a model more complex. This value over here is the number of nuts. Then what could be happen? Then if we have a low value over here, is because the k index, that is this value over here, it's not bigger than 1 or it's not very, very close to 1. Then when it happens, we are going to have here a value that is low and it is indicating with an asterisk. If it happens, then we have to increase the number of nuts. In this case, the model is good. Another important thing is related with the degrees of freedom. Remember that when we was working with linear models, the degrees of freedom are associated with the number of coefficients that we have, okay? In this case, how many coefficients we have? We have 29 coefficients. We can see that one if we are using this script, coef, and then we add here the model, this model. We can run this one, and we can see that we have 29 different coefficients. One coefficient for each function plus the intersect, okay? But when we are working with generalized additive models, the number of degrees of freedom that we have has a different name, and now is called as a effective degrees of freedom. And as you can see, the effective degrees of freedom are always smaller than the number of nuts we have in our model. Then the question is why we don't have 29 degrees of freedom. The point is, when we are working with generalized additive models and when we are using the NGCV package, this package over here for the GAM, the software is feeding the model on the data automatically, okay? And it provides the best fit. Then you can you can use the number of nuts you want. It doesn't matter, because at the end, the software is going to decide how many degrees of freedom you need in order to have the best fit on the data. And the best fit on the data using 29 nuts is going to be 17.2. And this one is going to be called as a effective degrees of freedom. In a very simple way, we can say that when we are working with generalized additive models, what we have is effective degrees of freedom. And this effective degrees of freedom is a kind of transformation of the number of nuts according to the best fit on the data. I like to think in the following way. For example, let's go to imagine that the number of nuts is the total number of resources that we have in order to fit the best model on the data. Then the software is taking from this 29 the number of degrees of freedom that it needs in order to make the best fit. And in this case is 17.2. But this number never can be bigger than 29, because 29 is the total number of resources that we have, okay? Then, for example, if the effective degrees of freedom is very close to the number of nuts, that's also not good, because it is indicating that in order to make the best fit, the software is taking most of all resources, and maybe that resources are not enough. Maybe even we need more effective degrees of freedom. But as there is no more resources, it has to take the maximum it can take, okay? Then we want to have some room between these two numbers. Here we have also, it is saying that one, right? Low p-values may indicate that k is too low, especially if effective degrees of freedom is close to the number of nuts, okay? Then what we need also is to have some room between these two numbers. Also, when using this script, we have 4 different graphs. The first graph is related with the response versus the fitted values. And in this case, what we want to see on this graph is the data are distributed like this, making a line of 45 degrees, okay? When it is happening, then the model is good. For the next graph, what we have is the histogram of the residuals. And here, what we want to have is a normal distribution of the data, and we don't want to have any outlier, and we want also the histogram pretty symmetric. And in this case, is good also. In this graph, that is the residuals versus the linear predictor, what we want is homoscedasticity. Remember that the homoscedasticity is the constant error for the variance, okay? And here we have homoscedasticity. Then in this case is also good. And the last graph is related with the QQ plot. With the QQ plot, what we want is the black dots to be very close to the red line. Remember that the red line is the ideal scenario for the normal distribution of the residuals. In this case, it's not that bad. Then, as a conclusion, we can say that this model that is using 29 nuts by default is good in general, okay? Because we have a p-value that is good, and also all the graphs are good. Then the model is good. But now there is the next thing, right? Because as bigger is the number of nuts, more complex is going to be the model. As more complex is the model, it is indicating that the model is more close to the data. It's more fit to the data, right? But what we don't want is to have something that is overfit, right? We want something that is pretty general, right? That's the reason because we call generalized additive models, right? Because we want something general, but we don't want to be very close to the data. Then as we have here some room, maybe we can decrease the number of nuts and we are still having a good model. And that one also is going to be good, because if we have a model that is not very close to the data, we are going to have some room for the spatial autocorrelation of the residuals. And if we have some room for the spatial autocorrelation of the residuals, we can apply an stochastic model that in this case is going to be the ordinary Kriging. then we can plus the generalized additive model with the ordinary Kriging, and we are going to have the regression Kriging. But if the model is pretty close to the residuals, it is not going to be any spatial autocorrelation. Then if there is no spatial autocorrelation, we cannot apply the ordinary Kriging. Then we cannot do regression Kriging, because at the end we cannot do the stochastic model, and then we have to take just the deterministic model. Then we want something at the limit, right? We want to have a good model. We want to have also very small spatial autocorrelation in order to apply ordinary Kriging, but we don't want to have too much spatial autocorrelation, because if we have too much spatial autocorrelation, the model is invalid, because we are violating the assumption related to the no spatial autocorrelation on the residuals. As I said at the previous video, we can have a very small spatial correlation, and that one is not going to be bad. But if we have a big spatial autocorrelation, we are going to violate the assumption, and then the model is going to be invalid. Then the next step is to play a little bit with the number of nuts for the model in order to see how flexible we can be, okay? Then we are going to create a new model, and that's the things I'm saying here, right? Can we improve the model? We can make an easy model with less nuts. The default is taking 29 nuts, but the effective degrees of freedom are 17.2. Then looks like there is some room. Then we are going to create a new model. This model is going to be named with this name, GAM model 1. And then in this case, we are going to start with 5 nuts to see what's going on. The rest of the things are going to be the same, the data set and the method that we are using. Then we can run this one. We can start from here. Then we can see the summary for this model. And here what we can see is now the degrees of freedom is 3.6, okay? And now this model can explain less variance than the other one, right? Remember that the other one, it was 95.6, something like that, okay? But now we have 90.2, okay? There is big difference. Also, we can see the summary of the residuals for this model. And as you can see here at the bottom, this one is pretty asymmetric, right? Because the maximum value is almost the double as the minimum value. Also, we can plot the histogram associated with this model, and we can see that one reflected over here, right? With this long tail in this area of the graph. Also, the mean value and the median, they are pretty distant, right? We can see the 3D interpretation of this model, and with 5 nuts, what we can see is that the plane is pretty flat, right? Before it has some shape, but now it's pretty flat. There is not too much nuts, right? To adjust the plane to the data set. And that is what we are going to see with the next script. As I said previously, now we have just 4 nuts, and the effective degrees of freedom is almost 4, right? That is indicating that the model is taking all the possible resources that have from the nuts in order to make the best fit. But even in this case, the fit is not good, right? Because as you can see, we have some asterisks here indicating that the model is invalid. Also, this value is pretty small to compare with the number 1. That is the goal that we want, or very close to 1. Also, we can see the graphs here is making a line of 45 degrees, but the data is a little bit more dispersed. The histogram is not really good because we have a very long tail over here that is going to affect the normal distribution of the residuals. For the constant error for the variance, we have a very high value over here compared with the other ones, right? That maybe is showing a little bit of heteroscedasticity, right? And the QQ plot, again, it's indicating that the data is not pretty normal distributed, right? then we can say that this model is no good. But now the next step, for example, is increase a little bit the number of nuts to see what's going on. We can increase to the number 8 and we can run again all this model. Now I'm going to be a little bit more fast. Then here we can see that we didn't improve too much the symmetry of the histogram. Now the mean and the median, they are a little bit more close, that's good. But for the minimum and maximum, there is big difference. We can see that one on the histogram. Also for the 3D model, we can see that now there is a little bit more shape on the plane, but it's still no good. Looks pretty flat, okay. And for the last script, again, we can see that it's almost taking all the resources from the nuts, right? And also we have here the asterisk indicating that the model is not good. Then the next step is to see what's going on with the number 10. We can run again all these ones. And now the histogram is quite symmetric. We have for the maximum value 128, for the minimum 101. The mean value and the median are pretty close, that's good. And also the first quantile and the third quantile has more or less the same amount. It is a pretty symmetric histogram. Now we can make the interpretation of the histogram, the representation of the histogram. And as we can see, it's pretty symmetric. Then we can see the model in 3D, and that one is not looking bad, right? It's a little bit better than before. And also we can run the next script to see what's going on. Now we have a valid model because we don't have any asterisk over here. The number is close to 1, and as we can see over here, it's taking almost all the resources, right? Because we have 9 nuts and it's taking 18, right? But the model is still good. Then here maybe 10 nuts is going to be the limit, right? We have to understand that it is 9 nuts plus the intercept, right? The intercept is going to be the total number of 10 nuts. Also, we can take a look on the diagnostic graphs. The first one that is related with the response versus the fitted values, the data is showing a distribution that is around 45 degrees. That is good. Then for the histogram, as I said previously, is pretty symmetric, showing a normal distribution. The homoscedasticity in this case is not that bad. We have a little bit high value over here, but looks pretty constant. And for the last graph is the QQ plot, and we can see that most of the dots are on the red line, indicating a normal distribution of the data. Then at the end, we are going to be analyzing the spatial autocorrelation of the residuals for 2 models. For this one, for this one. Remember that for this one, we leave the default value that is show 29 nuts. Okay, then we are going to add that value over here. To be honest, it's not 29, it's 30, because we have 29 functions plus the intersect. Okay, then we are going to run all these ones again to see how it looks like. We are going to go faster just to save the model properly. Okay, remember that this model it's representing 95.6 of the total variance of the data. Also, for the histogram, we have something pretty symmetric. As you can see over here, this one is the 3D interpretation. We can see that this model has more shape than the other one. We are going to compare now. Then also we have here these values indicating that the model is good. And as I said previously, we have in total 29 coefficients for all the functions, and also 1 extra coefficient for the intersect. Okay, then in total is going to be 30 nuts. That's what we can see over here, right? 29 plus the intersect total 30, and that's the value that we added over here. Now this model is going to be called as a GAM model. The next one is going to be GAM model number 1, and in this case we are going to use 10 nuts. Then we are going to run everything again just to make sure that everything is okay. In this case the model can explain 93.6 of the total variance of the data. Then the histogram is pretty symmetric, as we said. And now we can compare this model, this one, with this shape, with the other model. That it was this one over here. As you can see, this one shows more deep shape, right? You can see most over here and also over here. Now I'm going to show you the other one again. This one is a little bit more flat in these areas, also over here. And also here we have the last script for this model. And again, it's showing a valid model. Now then we are going to do the semivariogram for both of these models. Then first we are going to convert this data set a spatial point data frame in order to indicate to the software that X and Y are coordinates. Then we are going to use this script. With the next script, we are going to extract the residual values from this model. Then we can run from here. And we need the residual values in order to create the variogram or the semivariogram. And we're going to create the semivariogram with this name, okay? This object is going to have this name, body GAM, okay? What we have here, the script to create the variogram, and what we are saying that the residuals from this model are constant, and these residuals are located in this data set, that is the number 8, that is over here, the spatial point data frame. Then we can run this script, and now we can plot the results. Then here we have the semivariogram for the residual values that are coming from this model. Then here we have the lag distance, and the total lag distance is around 150,000. This total distance is just 1/4 of the total extension. Remember that for the total extension, we have from this point that it is the first data point to the last data point, more or less, we are going to have around 450,000, okay? Then 1/4 is going to be 150,000, and is the value that appears by default when we didn't specify anything here. Also, the lags, we have one lag every approximately 10,000 meters, okay? 10,000, 20,000, 30, 40, and 50,000 more or less is matching with this value over here. And here we have the semi-variance. And as you can see, this graph is not showing too much structure, right? It looks like we have here the seal, and looks pretty short structure over here. It is more like poor nugget effect, right? But now we can be close to this area over here where we have a potential structure on the residuals. That's what we're going to do with the next script. Then I'm going to create a new semivariogram with the same name, but I'm going to change the lag distance and also the lags. Then in this case, I'm using the same again script, the variogram, and I'm working with the residuals from this model, from the GAM model, that is the one that has k equal to 30, and I'm saying that the residuals are constant. The residuals are located in this data set, but now what I want is the cutoff to be equal to 60,000, okay? I want the graph until here, because this area is the one looks autocorrelated, right? But all these one are not interested because there is no correlation on this area. And also I want each lag every 6,000 meters, okay? A little bit less than 10,000 meters as this graph. Then let's go to run this script. Let's go to plot the graph. And as you can see, now we are at the correlated area, and it is not really clear that we have any correlation here. Looks like we have poor Nagel effect, right? Because we have something here, but we have just 14 points. It's not pretty strong, right? But we're going to try to use anyway this data, but looks there is no spatial autocorrelation when we have 30 nuts. Then with the next script, we're going to leave the software to try to fit any of these models on this data to see what's going on, okay? Then after doing that one, it fits the spherical model with a Nagel effect of 519, with a partial seal of 1186, and with one range of 15,936 meters. But it is saying that for most of these models, the software couldn't fit any model, because after 200 iterations, there was no convergence. Then we have the spherical model, but looks like for most of these models, there was no way to fit a model, okay? And that's important, right? It is indicating how complicated it is to fit a model on this data that looks pretty poor Nagel effect. Then with the next one, we are going to create the model, and we are going to create this model with this name, okay? We are going to use the fit variogram. We are going to use this variogram, and we are going to provide these values by default, because in order to start the computation of the creation of the model, we have to provide some values, okay? But these values are approximately. The first value is the partial seal. The second is the model. The third is the range, and the last one is related with the Nagel effect, okay? Then we can run this model, and now we can see the results of this model, and the results are pretty similar to the ones the software decide to take by default. They are pretty similar, right? And now we can plot the model on the data with the next script. And that's the model the software decide is the best according to this data. Then for this model here, we have the range until here approximately. That is almost 15,000 over here. Then we have the partial seal that goes from here to here, okay? And the amount is 1,300 almost. And also the Nagel effect is close to 500. And the seal is going to be the partial seal that is from here to here, plus the Nagel effect that is from here to here. As a conclusion, we can say that this model doesn't show a very strong spatial autocorrelation, right? Because looks pretty poor Nagel effect where we don't have any structure, but we fit a model anyway, okay? Now let's go to see what happened with the other model. Remember that the other model is this one, and in this case we was using a k equal to 10 in order to leave more room between the model and the observation and data, okay? Then first we are going to run this line where we are going to extract the residual values from this model. Then we are going to create the semivariogram, but in this case we are going to call that one as a vari-gam number 1, okay? Remember that the other one, it was vari-gam. Then in this case we are going to use the script variogram to create the semivariogram, and what we are saying is that the residuals from this model are constant and they are located in this data set. Then we can run the next line, and now we can make a plot. And that one is for an extension of 150,000. As before, it is 1/4 of the total extension. And also now we have a lag distance every 10,000 meters, okay? This value approximately goes to 50,000. And now what we can see is a little bit more structure than before. As you can see now, this one is longer than before. I can plot the other one. It was this one over here to show the difference. Okay, that one is the, no. Oh, because I changed here the name. Okay, it doesn't matter. We can run this one again. I can run this one and I can run this one. And now we have the graph, right? This one is for 30K. As you can see, it has this shape. The important thing is this area over here. And this one is for 10K. We can see that this distance is longer, showing a little bit of more structure in this semivariogram. Okay. Now we can be focused on the correlated area that we are assuming that is around 60,000. Okay. Then we are going to create a new semivariogram with the same name, but we are going to change the cutoff to 60,000 to have the graph over here approximately, and also to have a lag distance every 6,000. But let me run this one again, because later I want to compare this one with this one, okay? Then I'm going to run this one, and this one, this one, and this one, and this one. Going to run all these ones again. And now we are going to do the variogram, just focus on the 60,000 for the lag distance. Then I'm going to run this one and plot the graph. Okay, and this one, as you can see, has a little bit more of a structure, but also looks like poor nugget effect. We can compare this one, that it comes from the 10K, to the other one that comes from 30K. Okay, let me run this one. Okay, you can see this one goes until here, doesn't reach 2,500, but the other one goes a little bit higher. You see, it can pass the 2,000. Then at it passed the 2,000, we have a bigger range, right, over here. Okay, this one is the 30K, and this one is the 10K. These ones pass a little bit the 2,000. They are pretty similar, right? But that one has more structure, but not that much. Again, looks pretty poor nugget effect. Then we can run the models. First, I'm going to run this script in order to leave the software to decide what is the best model for this data set. Then, oh, sorry, here there is a mistake. I have to add here number 1 and also here number 1. Then we can run this one. And as you can see, the software is taking the spherical model, but with a little bit more of range. Right before, it was this one, a spherical model with this range. That one is from the 30K. And this one is from the 10K. There is no big difference, right? It's pretty similar. And also, the software has a lot of problems to fit the model as before, right? Then we can do the model now with this script. We provide these values that are approximately. And now we can see the results. And we have almost the same. And now we can plot the model. And again, in this case, even when we are taking 10 nuts, the spatial structure of the residuals are not really good, because looks pretty poor nugget effect. Then there is no big difference when we are taking 10 nuts instead to take 30 nuts, okay? Because we don't have too much spatial structure, and we don't know if that very small structure is going to be good enough in order to do the ordinary kriging. We are going to try, and we are going to see what are the results. Now, the next step is to create the raster file associated with the model. Remember that in order to do that one, we need to create a grid to interpolate inside of that grid the predicted values associated with the GAM model. Then first we have to load and create the grid, right? We are going to use the grid that we created at the part 1 of the Regression Kriging lesson, okay? That one, it was named as a how to create a grid using a shapefile with R and QGIS, okay? I'm not going to do this one step by step because we did already in that lesson and it's going to take very long. What I'm going to do is select all this section and run all together until here. And now we are going to use this grid that has this amount of cells. Each cell is 500 by 500 to predict the GAM model. Then we can go here and run the next scripts. With this script, we are going to do the GAM prediction, and we are going to use this script over here. The name of this object is going to be this one, GAM prediction. And then we are going to use the GAM model. This GAM model, remember that it was the one with 30K. And we are going to use the grid that we created here at the top. Is this grid over here. And that's it. Then we can run this one and run the next line. Then we can see now a summary of this object over here. What we can have in this summary is showing that we have this amount of cells, and in these cells what we have is the fitted values, and also we have the standard error associated with the predicted values or fitted values. Now what we are going to do is convert the grid a spatial point data frame. As you can see, this grid over here is this grid over here, and it is a data frame. Okay, now we are going to convert this data frame a spatial point data frame using this script over here. The next thing that we are going to do is create the grid with the predicted values as a spatial point data frame, and we are going to use this script over here. Just you have to follow just the step by step because there is a lot of information, and sometimes these scripts are not easy to understand, but just follow the steps. Okay, if you are following all the steps, you are going to be successful. Then at the end, what we are going to do is convert the grid a spatial pixel data frame. The objects are points in a regular grid. Okay, then we are going to do this one and run also the next one, improving the computational efficiency by using the full grid. Then we are using the full grid for the new grid, that is this one. Then run this object over here, and now we are going to assign the reference coordinate systems. We want this reference coordinate systems that is going to be added to this grid over here. Then run this object also, and this one. And now we can check the statistics associated with the new grid. Remember that this new grid has already inside of each cell the predicted values for the GAM and also the standard error for the GAM. Then we can run this one and see the results. This information is related with the cells. This one is related with the reference coordinate systems that we add to that grid, and this information is related with the fitted values and the standard error for the fitted values. Here we have the minimum, the first quantile, the median, the mean, the third quantile, and the maximum. Then now we can move to the next script where we are going to create a graph where we plot just the fitted values that are the predicted values, okay, from the generalized additive model. Then we are going to use this script over here. We want this object to be named with this name, and we are using this script where we plot the predicted grid, that is the grid, but what we want to see just is the fitted values. Then we can run the script to visualize the graph. And now we have to leave the software to load that data. And here we have the deterministic model associated with the generalized additive models when the number of nuts is equal to 30. Now we are going to convert the new grid as data frame in order to manipulate the variables inside the grid. Then we are going to create a new object that is going to be a data frame of this grid over here. Then we can run this one. Sorry. No, just this one, all the line. And also we want to view that data frame. Is this data frame. As this data frame is now well organized, we are going to change the organization. What we want is the X and Y values, and then the fit, and then the standard error. Then to do that one, we are going to use the next script. Fix the order of the columns. Then we are going to use a new name for this new grid that is going to be this one. And we are going to use this script to change the position of the columns. Then run and run. Now you can see that now we have first the X, then the Y, then the fit, and then the standard error for the fitted values. The next thing that we are going to do is create a raster with the new data set, that is the predict grid number 3, is this one over here, to be exported to QGIS. In order to do that one, we have to load the raster library. Then we are going to run this script. And then we are going to create an object that is going to be with this name, that is a raster file. And we want this raster file with this information. Then we are going to run that one. And now we can plot the this raster file on RStudio. Trend surface and standard error maps. Then we can run this script and wait the software to load the data. And we can make this one bigger. Then here we have the fitted values. This model is the same as this one over here. Let me show you as this one, okay? But in different format. This one is a raster file. And this one is for the standard error of the fitted values. Now with the next script, we are going to export this raster file. First, we are going to run this line and we are going to run this script in order to see what is the folder where this document, the raster file, is going to be saved. If we want to change the folder, we can use this script over here. And I want to change that one. I want to use a different folder. I'm going to use the raster file saved here in this folder. Then I'm going to select all this one. Copy. And I'm going to put over here. Paste. And I'm going to change now the direction of the dash bar. It has to be the opposite one. Because in other way it's not going to work, okay? Then change all these ones. And now we are ready to run this script. In this way we can add this directory, okay? Then that one is good. And now with the next script we are going to save the raster file. That is this object. This object is the same as this one. And we are going to save with this name. Then I don't want any null value. And overbreed is going to be true. Then we can run this script. And now we can see the list of the documents inside of this folder. And as you can see, now we have that raster file over here. That is in this folder over here, this raster file. Now what we are going to do is open this new raster file in QGIS. Then go here, add, is a raster, then look for the folder, is this folder, select the file, open, and add, and close. Then we can move to the top. Where is this one here? Move to the top, and here we are going to assign the reference coordinate systems. That is going to be the same as this one. 32, 613 is this one over here, and OK. Now we can see here that we have two bands. One band is for the predicted values and the other band is for the standard error of the predicted values. Then we can modify that one in properties. We can select just one band, apply. Then we can change here the to single band color. Then select a ramp. We can use, for example, this one. Select discrete intervals. I'm going to use a different one. Let me see. This one over here. Then I want equal interval and I want 10 intervals. And then apply and OK. And that's the model. Now we can add the standard error. Then we are going to load again the same map. Close. We are going to add the coordinates. That is these coordinates. OK. Now we can go to properties. Then change for a single pseudo color. Here we can change the other band. And we can choose this one over here and also 10 or equal intervals with 10 classes and apply. And that's the map for the error, right? As dark is the color, the error is smaller, and clear is the color, bigger is the error. With the red colors, we have the highest values for the error. Apply and OK. Then where we have more data points, I'm going to put the data set on the top, is where we are going to have the minimal error, right? Here we have a lot of data points, we have low error. The same here and the same here. The areas where we don't have data points is where we are going to have the biggest error. All these areas over here, and that's it, right? Related with the error. And this model is related with the trend surface. Then also here we can change for the same color as the other models, right? Because this one has a different color. Then we can go to properties and assign the same color. Then go here, more colors, and it's this one. Apply and OK. And now this one has the same color as the other models. Now the next thing I want to do is a 3D visualization of the general additive model with the observed values. And in order to do that one, we have to remove here one of the bands. Because when I have two bands as here, one band for the deterministic model and the other band for the error associated with that deterministic model, the plugin that I'm going to use to do the 3D visualization of the model, that is this plugin, let me show you, this one, QGIS 23JS, it doesn't work properly because it has two different bands and the software doesn't recognize this file as a digital elevation model. Then what we are going to do is remove just one band and work only with the deterministic model. Then what we are going to do is to use an script to remove that band. I started a new session and I loaded already all the layers and data sets. The last thing we was doing last time, it was this script over here to export the raster file. And now what we are going to do is to use this package to remove the standard error band for our raster. Remember that now we are working with this grid. And this grid has this information, the X, the Y, the predicted values of fitted values, and the standard error associated with these fitted values. And we want to remove this column from this data set. Then we are going to load this library to do that one. Then run. And now I'm going to create a new grid. But in this case, what I'm saying is I want this new grid with this name, and I'm using this grid, that is the one I showed you previously, but I want to take this one out. Then I can run that one, and now see the results. And as you can see, now we have just the X, Y, and the fitted values. Now what I'm going to do is create a new raster file that is going to be with this object name. This one is the script to create a raster file with the new grid, that is this one, and I'm going to export as a TIFF with this name. Then I'm going to run from here. It's going to be saved in the same folder as before. And here I can run to see the files I have in this folder. And as you can see, the new one is this one. Now I can load this raster file, that is a digital elevation model, on QGIS. Then I can go to QGIS, add a new raster, look for that one, that is this one over here, and open and add, close. We can add the reference coordinate systems, that is this one. Okay. Now we can go to properties, and as you can see, this new raster file has just one band. We can do the same as before, single band pseudo color, select here the ramp color that we want, that is going to be this one, then equal intervals, 10 classes, apply, and we can put here also discrete. And that's it. Now we have the raster with just one band, and this raster can be opened with the plugin QGIS 23JS to see the 3D interpretation of the model. Before to start with the 3D visualization, remember that this deterministic model, let me put over here, let me change this name here, rename layer, is associated with the 29 nuts, okay? And now I want to do the same model but with the 10 nuts. Then what we can do is go here, go to the line 170 and this 173, and here instead to use this model, that this one is for the 29 nuts, what we are going to do is add here the dash 1 to work with the 10 nuts, okay? Because I want to use the two deterministic models to see the differences, right? Remember that we have these two models saved here, okay? Let me show you. We have this model and we have this model, and they are different models, right? This one is for the 29 nuts and this one is for the 10 nuts. And now we are going to do the same but for the 10 nuts. In this case, I'm going to cut the video now and I'm going to show you the final model, because at the end it's going to be the same that we did for this model, but just for the model 1, okay? Then you have to change here the name, whatever you want, right, to create the new raster file. But the thing is changing is this one, okay? Now here we have already the new deterministic model, the generalized additive model with 10 nuts, okay? I put here GAM model fit K10, okay? And also we have with 29 nuts. Then if I take this one, you're going to see the difference between these two models. The main difference is over here, right? And also over here. For all this area, they are pretty similar, as you can see. And now what we're going to do is visualize these two models in 3 dimensions. But first, let me load the perimeter of this raster file in order to do the 3D interpretation properly, okay? Then I'm going to load the vector file associated with the perimeter. Is the shapefile perimeter, this one, okay? Add and close, and I'm going to make this one transparent. Properties, And now you are going to see how we can use that one. Okay, transparent, apply, and okay. It's just a line. Okay, if we take this one out and all these ones out, you are going to see the perimeter. Okay, it's just a perimeter. Then we can leave, we can close this one also, leave this one and this one. Remember that this perimeter was created in this lesson, okay, where we was talking about how to create a grid using a shapefile with R and QGIS. Then if you want to know how to create this perimeter, just check this lesson. Then to see the 3D of this model, we are going to use this plugin, as I said previously, the QGIS 23JS. But what I saw when I was using the virtual computer, because I'm using a virtual computer, it is just an Oracle virtual machine. This plugin doesn't work properly. As you can see here, this message, I tried to figure out how I can fix this issue, because I remember previously I was working with this plugin with a virtual machine and I didn't have any problem. But now I couldn't figure out what's going on. And currently, I cannot have any 3D visualization when I'm working with the virtual machine. Then what I did is export the project to my regular computer, and now we are going to see the 3D visualization in that computer. I believe the problem has to be something related with incompatibilities of any software that I have installed in the virtual machine. I'm not sure, but I cannot waste too much time trying to identify what could be the issue. Then I'm going to bring here the project in my regular computer. It is the same layers, the same things, but now instead to work with the virtual machine, I'm working with my regular computer. Then first thing that we are going to do is install the plugin. Then go to the plugins, and it is this plugin. Just put QGIS 2T and you are going to have this one. Select the plugin and install the plugin. Remember that you need internet connection in order to install the plugins. Then close. And go here to web, and it is this plugin. Then select the plugin, and it directly loads the layer. As you can see, this layer is totally flat. Then we have to do some modifications. To work with this plugin, it's not pretty easy, to get the exactly configuration you want to reproduce the 3D interpretation of the data. Sometimes it's not easy. It's just playing with the parameters and see what is the results. Then first we are going to go to scene settings, and here we are going to add some exaggeration on the zeta. Okay, in this case we are going to add 200, apply, and okay. Now as you can see, we can start to see some 3D effect. Okay, then the next step is to work on the raster file. We are working now with the 10K for the nuts. Then go to properties, and here what we are going to do is add transparent background. Apply, and okay. And now in order to avoid to have these very ugly lines over here, we can modify the perimeter. That's the reason, because we load the perimeter in order to have something more nice. Okay, then also we can go here, zoom to the layer to put the layer on the center. Okay, that is very important in order to manipulate properly the rotation of the 3D model. Then now we can go to here to the perimeter. Let's go to minimize this screen, and we want to have a perimeter that is a little bit smaller than this one in order to avoid those ugly lines. Then press the pencil to edit, but first let's go to export this one, because I don't want to modify the original one, right? I want to create a new one, and this one is going to be perimeter 2. Then save in the folder you want, or just press OK to save in the folder by default. Then OK, And now we can edit this perimeter properties. Let's go to put this one transparent, apply, and OK. And now select this one, press the pencil, and we are going to deal with this toolbar over here. If you don't have this toolbar, just go here, click right on your mouse, and select Advanced Digitalizing Toolbars, okay? And we are going to use this tool over here. Then select the exterior part of the perimeter, click, and make this perimeter smaller. And OK, and now we can save. Press the pencil again, save. And now we are going to use this perimeter to create the model. Then let's go to the model again. And now go to Properties. And here click then with polygon raster, with polygon layer, sorry. Select and select the perimeter number 2. Apply and OK. Now let's go to leave some time to the computer lower the layer. And this one is the result. Now you cannot see that ugly lines, and now the model is pretty nice. We can have a 3D interpretation of the surface of the groundwater that is pretty nice, and it goes pretty smooth, right? Now also what we can do is add the data set. Is going to be this one, okay? And here we have to do also some modifications. Let's go to Properties. And here what we want to select is zeta values. And also the mode, what we want is to have absolute. Here you can change the dimension of the dots. For example, for 3000. And also we can change the color here. Expression. And select a different color. For example, we can select a red color for the data. Oh, it's going to be confusing with the background, right? With the 3D model. Then we can use a black. Okay, and apply. Even we can make the dots smaller. 2000. Apply and OK. And then here with the black dots, what we have is the observed values. And remember that the distance from the plane to the observed values is the residual values, okay? Then we can make zoom to the model. And as you can see, we have an excellent 3D visualization of the observed values with the model integrated. Now we can take this one out. This one is for the 10K, and we can work with the 29K. Then let me make some modifications here. Apply. Sometimes the layer doesn't load, then you have to change the resample level, and then it's going to load again, okay? Apply. And okay. And now here we have the other model. This one is for 29K. Then you can play with the exaggeration, right? Settings, maybe for example for a 100. But as you are changing that one, you know, the plane is going to be more flat, right? But it's going to be even more realistic. But then you cannot see the 3D effect really well. Then sometimes it's better to put a little bit more exaggerated. Let's go to see 150 to have a nice interpretation, right, of the model with the data set. I believe this one is a very powerful tool to see the 3D interpretation of your results, and it is something that it's not available on R, right? The 3D interpretations that we have with R, they are very poor, and it is nothing compared with this one, right? That you can move 360 degrees and you can change the exaggeration. You can do a lot of things with this tool, right? And it is amazing. Okay, now what we are going to do is the Kriging, the ordinary Kriging for the residual values associated with the 10K and the 29K, okay? Then we are going to do two different ordinary Krigings. Then at the end, we are going to plus the deterministic model, that is the generalized additive models, in this case is this one, plus the ordinary Kriging, that is the stochastic model. And that is going to be the next part of this video. Now I'm going to create a new data set. I'm going to create a table with the residuals to perform the ordinary Kriging. Then I'm going to call this table with this name. And this table at the beginning is going to be the same as this table over here. Let me show you this table. Is this one over here. And this table has the X and Y and the groundwater elevation, okay? That's the original table, but it's the backup that we created at the beginning. Then let's go to run this script. And then I'm going to add the residual values to the new table. First, we are going to work with this model. Remember that this model is for the 29 nuts. Then I'm going to add this one. Then I'm going to say that these residuals from this model are going to have this name. Then with this script over here, I'm going to add that residuals to that table, this new table that we created. This one is already run. I'm going to run this one. Also, I'm going to add the predicted values to the same table. Then I'm going to say that the predicted values has this name over here. And with this script, this one here, I'm going to add the predicted values to the table. Then residuals, I'm going to add this one, run this one, and this one. Now also I'm going to add a quality control. The quality control is that the predicted values plus the residual values has to be equal to the groundwater elevation, okay? Then run this one, and now I can see the new table. Okay, we have X, Y, the groundwater elevation, the residual values, the predicted values, and this one plus this one is going to be equal to the quality control, that in this case is going to be the groundwater elevation. Then this column and this column has to present the same values, just to make sure that everything is okay. Then if you want to export this table to a spreadsheet, you can use the next script over here, but I'm not going to do it. Now we are going to create the variogram model associated with the residuals from the 29K. Then first I'm going to create a backup of the table that we created. Let me go to run this one. We created the backup of the table that is going to be called with this name. And now I'm going to convert this new table as a spatial point data frame to indicate to the software that the X and Y are coordinates. I'm doing that one with the next script. Now let's see the structure of the residuals. Then I'm going to create an object with this name that is going to be a variogram. In this case, I'm using the residuals from the new table, and I'm saying that these residuals are constant, doesn't have any trend. And this data is located in this new table. This new table is this one that we created. And we can run this one. And now we can plot the variogram. In fact, this variogram is the same as the one that we created at the beginning of the lesson, right? Remember when we was doing the analysis of the different models and we analyzed the residuals? We already did this task. The only difference is that now we have the residuals inside of a data frame, okay? And before we was working directly with the residuals. Then the next step is to work just with the correlated area of the semivariogram. And that's the next script. That's because we put a cutoff of 60,000 and a width of 6,000. That is the lag distance for each lag. Then we can run this one and plot the graph. That is supposed to be the correlated area. As we said previously, looks like poor Nagar effect, okay? Then with the next script, we allow the software to fit a model automatically, right? not to fit a model. Decide what is the model that fits the better on the data, okay? Then we can run this one. And as we said previously, there are a lot of models that cannot be fit, okay? Because after 200 iterations doesn't fit well. Only the spherical model for these parameters is the one who is working well, okay? Then now we have to create the model. In order to create the model, we are going to put this name, and we are going to use this script over here. With this script, we can fit a model on the data. Then we are going to specify what is the variogram. In this case, it's this variogram. And we want to put initial values for the model. That is going to be these initial values. These values has not to be exactly, it's just an approximation that is going to help the software to start the computation for fitting the model. Then we can run this one. And now we can see the results. As you can see, these results and these results over here, these results here and these results here are pretty similar, okay? Then we can plot now the model. At this point, I want to clarify that here we are doing a very fast analysis of the structure of the data. We are not doing any cross-validation. We are not trying to fit any model manually. We are not trying to change the parameters to have a better fit. You know, all this stuff is already explained at the lesson first of this fourth geostatistic course, where we was talking about ordinary Kriging, okay? I don't want to do a full analysis because it's going to be a very long video, and you have already all the information. Here at the first lesson, we did a deep analysis. Also at the third geostatistic course, we was talking about the structure of the data. You have a lot of information over there, and I cannot spend more time talking about how you can do a proper analysis of the data for ordinary Kriging. If you want to have more information, I recommend you to watch the previous tutorials, okay? Now that we have already the model that we are going to use, that is going to be this model, we can do the ordinary Kriging. We can do the interpolation, okay? And then we are going to use this script over here. We can start to run this one. And here is saying ordinary Kriging, residuals, generalized additive models, okay? Then we are going to use the residual values from the generalized additive models to create the ordinary Kriging. Then first, let's go to start with the surface prediction, okay? With this script, we are going to predict the values in those locations where we don't have any sample. How we are going to do that one? Using this script. What I have inside this script? We have the residuals that is showing they are constant. They are not having any trend. Also, we have to specify where the data is located in this table. Also, the grid that we are going to use, that is going to do this, is going to be this one. And also, what kind of a structure of the data we have, and it is this model, the model that we created over here. Then also we can see a summary of the new object, that is the prediction using this data. And here we have the information. We have the predicted values, and also we have the errors associated to this prediction, okay? Then we have to convert this data set to a spatial point data frame, but we already did previously. Then we cannot repeat that one, okay? We have not to do that one again. That is because I put this one over here. Then with the next one, let me run this line. With the next one, create the grid with the predicted values as a spatial point data frame. Then we are using this script over here to do that one. As you can see in this script, is specifying a spatial point data frame, okay? Then the next one, all these steps it's pretty similar as the one that we did when we created the deterministic model. But in this case, it's just for the Kriging, okay? Then we are going to convert the grid a spatial point data frame. The object are points in a regular grid, okay? Then we can run this one, improving the computational efficiency by using the full grid. Then we can run this one, add the coordinates to the new surface. This one, checking the statistics and characteristics of the new grid with a summary. Also create a graph where we plot just the fitted, the predicted values. Well, here it's not going to be the fitted, it's going to be just the ordinary Kriging, okay? Just create a graph where we plot the predictions, the predicted values, right, for the ordinary Kriging. Plot the predicted values from ordinary Kriging. Then we can run this one, and now we can print the graph. And this one is the result. As you can see, the Kriging prediction has all these features over here that we are going to see what is that, okay, later. Now convert the grid a data frame in order to manipulate the variables. We want to manipulate some variables inside this grid, and then we have to convert the spatial point data frame that we have in a regular data frame. To do that one, we are going to use this script. Then now we can see the new data frame is this one. What we have here, the X, Y, the predicted variables, and the standard error. And also we have the X and Y, there are repetitive values because here we have the same information. Then with the next one, what we are going to do is removing the variance error in order to have a 3D visualization with the QGIS to 3JS as we did previously with the other model. Remember that when this raster file has two bands, we cannot open that one with the plugin, and then we cannot analyze the 3D visualization of the raster file, right? Then we are going to use this script to remove all these values. We want to remove the standard error, and we want to remove, well, the variance, also the X, this one, sorry, and the Y that is duplicate on this data set. Then we can run this script over here, and now we can see the new table is this one. Now we have the X, Y, and just the predicted values for the ordinary Kriging. The next thing is to create a raster file. We are going to do that one with this script over here. Then we can run this line over here, and now we can save with this name. We are going to export and save with this name. And now we can run the list to see if that is saved properly. Is GAM, ordinary Kriging, GAM-TIFF is this model over here. Now we can open this new raster file in QGIS. Then we can go to QGIS, close these windows, and here add the new raster file. This one. And it's going to be ordinary Kriging, GAM, open, add, and close. And here we can add the reference coordinate systems, is this one, okay. And we can do some modifications here, properties. We can leave this one with discrete and equal intervals, 10 intervals. And apply, and OK. And now these circles are the structure that we have, and then if we measure the distance of that structures in meters, okay, as you can see, these structures has around 22,000. New one, for example, this one over here, 22,000. This one that is smaller over here, 11,000, you know, between 10,000 and 20,000. And that's the structure that we get here in this model, right? The range is until here. The range, let me see over here, is this one, this range, right? Almost 15,000. And that's the information that we can see over here. Okay, all these circles has a distance between 10,000 and 20,000, and is the structure that we have in our data. That very small structure makes these circles on the ordinary Kriging. Then the next step is to add the GAM model with the 29 nuts plus the ordinary Kriging associated with the residuals of this model. Then to plus these two models, we are going to go to raster calculator, and here we are going to select the nut with 29K, that is this one, double click, plus the ordinary Kriging that we created with the residuals from this model, that is this one, ordinary Kriging GAM. Then we are going to save this one in this folder over here, and we are going to call this one, for example, GAM K29 plus. We cannot use the symbol plus because it's not going to be accepted by the software. Then here, ordinary Kriging, then save, and OK. And now this one is the regression Kriging, right? Then we can change here the properties, single band pseudo color, here discrete, equal, and 10 intervals. Apply and OK. And now I'm going to do the same but for the 10K, okay? But I'm not going to record that one because it's going to make a very long video. Then I'm going to stop the video here. I'm going to create that regression Kriging with the 10K, and then I'm going to show you to compare the two models. I'm back, and here we have the model associated with the 10K plus the ordinary Kriging. As you can see, we can compare this one with 10 nuts with the other one, that is this one, with 29 nuts. And now you can see the differences between these two models. Remember that the model with 29 nuts is more close to the data. Then we have less spatial structure. And with the model that has 10K, is this one, there is more room between the model and the observed values, okay? The model is not too much fit on the data. But the differences between these two models is not that much, because for 10K, the structure that we have is 17,000, and for the other one, it was just 15,000. Then there is not too much differences between these two models. And the differences is the one that you can see over here. Also, let me show you. This one is the ordinary Kriging for the 29K. And this one is the ordinary Kriging for 10K. As you can see, there is not too much differences between these two models. Then the final result, the final regression Kriging, is not going to be very different, right? In fact, here, as you can see, I changed the name, right? I put regression Kriging, GAM for 29K, plus the ordinary Kriging. And the other one is this one, that is regression Kriging, GAM with 10 nuts plus ordinary Kriging. And both of them are pretty similar, right? If we take this one also, put this one, and this one, okay? There is not too much differences, right? They are pretty similar. Now we can see these models on 3D. Let me bring again the other computer here. And let's go to open the 3D visualization. Then go to here, QGIS. And first I want to work with the regression kriging with 29 nuts. Then go to properties. And this one is the model. Let's go to make some modifications here as we did previously. Let's go to select the perimeter 2. And we can take this one also, apply, and OK. And here is the model also. I would like to remove this one at the moment. And this one is the model. As you can see, this model, it's not really good. With the shape, we can see better, right? Properties, here, with the shading. Apply, and OK. You can see as we have a very small structure on the residuals, we have this kind of bumps, right? And that is not realistic with the model, okay? That's not good. It is indicating that the model that we get when we are using the GAM plus the ordinary kriging, these things, this shape that we can see over here are not good for the model. Then this model is not valid because it's not realistic. Okay. Then in this case, if you want to use the generalized additive models, you cannot add the ordinary kriging on the top because the result is not good. Then in this case, we are not going to use the regression kriging. In this case, we are going to use just the GAM with the 29 nuts. Is this one. But we have to take the other one. Let me take this one out, and this one. GAM model fit with 29 nuts. That's the one we want to see over here. Is this one. This model is good because we cannot see weird things, right? But when we add the ordinary kriging on the top associated with the residuals, we get that bands that make a model that is not realistic, okay? And if we visualize the regression kriging with the deterministic model, that is the generalized additive model with 10 nuts plus the ordinary kriging, again, the results are not really good. You can see the bands again, okay? It's not something realistic. We get a result because we're forced to get this result, but it's not good. It's not something good. We cannot apply in this case the generalized additive models plus the ordinary kriging because the result is not good. If you want to use the generalized additive models, my recommendation is just to use the deterministic model without the stochastic models. Later we are going to compare a deterministic model from generalized additive models with the regression kriging with the generalized least squares plus ordinary kriging. And you are going to see how the deterministic model from the generalized additive models is pretty similar to the regression kriging with the generalized least squares plus ordinary kriging. Now that we know that we cannot apply regression kriging using GAM in this case, we are going to see how we can apply the regression kriging using a different deterministic model. In this case, it's going to be the generalized least squares. Okay, remember that we created the generalized least squares in the third part of the third lesson of the fourth geostatistics course. It was this lesson over here. Now we are going to use that data that we created in that lesson to do the regression kriging with the generalized least squares. Then first, what I'm going to do is to load the data set associated with that residuals from the generalized least squares, okay? If you know how to get that residuals from that model, just check that lesson, okay? This lesson over here, everything is explained in this lesson. Then we can run this one. the directory is no good, then we have to look where is that spreadsheet. Then let me go here. It was generalized least squares, dataset. It was this one. Then copy this link over here, go to R, paste over here, and let's go to change the direction of this dash for the other direction. Remember that if we leave this direction, it's not going to work properly. Then change all these ones. And now it's supposed has to work, okay? Let me try again. Okay, now we have the data set. Let's go to create a backup. The next thing is to convert the data frame as a spatial point data frame to make the variogram. Then now we can create the variogram with the residuals from the generalized least squares. Remember that this one is a linear model, okay? Then plot the variogram, and this one is the variogram. As you can see, this variogram has a lot of structure. If you compare with the structure that we get from the generalized additive models, in that case, we have a range that it was 15,000. But look at this one, right? Looks like has a range that is more than 100,000. Then now we can fit this script in order to see what is the best fit according to the software, and it's using an exponential model that is this amount. However, this model is not good, because as we can see on the graph, the range is approximately over here, right? Where we can see that the semivariogram is increasing, then reach here the seal, and then stabilize the values, okay? Then from my point of view, the range has to be over here. Then a range that is this amount, it's not realistic, because we have to understand that when we are using the exponential model, the value that we get over here is the effective value, the effective range, and this one, it's not the real range. We have to multiply this value by 3, and when we multiply this value by 3, we are going to have 300,000, and 300,000 is almost all the extension of the data that we have. If you measure from here to here, you can see that we have 400,000, a little bit more, right? But for a range of 300,000, we have a range until here, and that's the almost all the extension, right? And that is not realistic. We already was talking about this issue when we was doing the lesson related with the generalized least squares, but here the value that the software provides doesn't convince me, okay? And that's the reason because I decided to use a different model, and in this case I propose to use the spherical model, okay? And I provide these values by default just to help the software to initiate the computation, right? But you are going to see that now the software propose a different values for the structure, and when we run the next script, we are going to have the values associated with the spherical model. And as you can see, for the spherical model, it proposed a range that is 150,000, and that one, it makes more sense, okay? Because it's a range over here, makes sense. We have these two values over here, okay? Doesn't matter. Then the software make the interpretation that the range goes here, get until here, and then stabilize over here, right? And also that is good for me. Even we can try to put here some values for the cutoff to see all the extension, right? We can put here, for example, for 400,000 and run this one to see all the extension, right? Then we can plot this one. Sorry, I make a mistake. I put 40,000, has to be 400,000, okay? Then we can run this one again, and that one make more sense, right? And the software is assuming that we have the range over here, and from here the values start to stabilize, okay? And it makes sense according to this information that we have over here. But a range of 300,000 over here with the exponential model, it doesn't make any sense, okay? And that's because we have to make the interpretation of the data and not just believe what the software is saying, right? Then let's go to see again the other model, this one. Then we are going to take a spherical model with these parameters over here, right? Then we are going to have an agar effect that is a little bit more than 1000, that is going to be over here. Then we have the partial seal that is around 3000, and a range that is around 150,000. And this range is the real one. We don't have to multiply in this case by 3. When we are using the spherical model, the range that we get is the real one. We have to multiply by 3 only when we are using the exponential model, okay? Then with the next script, we can plot the model on the data. And that's the model that we are going to have. But because I added here the 400,000 is taking all the graph, right? But as we usually say, we don't need to put all the extension, right? We want just 1/4 of the extension, that's enough. Then I'm going to run these ones again to have a more nice graph. That is this one, okay? Now the next step is to create the Kriging interpolation associated with the residuals from the generalized least squares. And that's what we are going to do now. Then we can run this one. And now we can see the summary. But we are using this script. We are using the residuals from the generalized least squares. And we are saying that these residuals has no trend. Also, this one is the data set that we are using. This data set is where these residuals are located. We are using this grid. We created this grid previously, right? And we are using this model. This model is this model over here that is related with the structure of our data. Then we can see a summary as we did before for the other model. Here we have the characteristics of the grid, and here we have the values that we interpolate inside that grid. We have the predicted values for the ordinary Kriging, and we have the variance, is the error for the these predicted values. Then we are going to do now the convert the grid a spatial point data frame. Also, we are going all these scripts is the same as before, okay? Then we are going to run all these ones. Let's go to add the coordinates. Let's go to see a summary of the new grid. Has all this information. Then let's go to plot the graph associated with the ordinary Kriging for the residuals of the generalized least squares. Now, as you can see, the structure that we have is too much big compared with the structure that we have with the generalized additive models, right? And that structure is associated with a range of 150,000, right? Then we can run the next script to change the variables inside the grid. We can see that the information that we have here is the x, y, the predicted and the variance, and also the x and y that is repetitive, right? Then we want to remove this one, and this one in order to see the 3D visualization, right? Then to remove that columns, we are going to use this script. And we can visualize the new data frame, is this one. And now we are going to export that data frame as a raster in order to have a raster file. Then we can run this one. And now we are going to export this raster file with this name, okay? That is going to be ordinary Kriging for the generalized least squares. And we are going to save in this folder where we have this new raster file. Is this one over here. Now we can open the raster file in QGIS. Then go here, add the raster file, raster, and it's going to be this one over here. Open, add, and close. We can add the reference coordinate systems. That is this one. Okay. And now we can make some modifications here to properties. Single pseudo color, discrete, 10 intervals, and apply, and OK. Next step is to plus this value over here, this raster, plus this train surface over here. Let me take this one out. This surface is from the second order train surface from the deterministic model using the generalized least squares. Now we are going to plus this model plus the ordinary Kriging that we created, plus this one. Then let's go to the raster calculator. We want to select the second order train surface from the generalized least squares plus the ordinary Kriging from the generalized least squares from the residuals, right? And we can save this one with the Regression Kriging, generalized least squares, ordinary Kriging. Save, and I don't know why it's marking this one, the reference coordinate systems, but it's this one, OK, and OK. And now we have the model over here, we can put on the top, and change here the properties. Here is going to be single band pseudo color, here is going to be discrete, here is going to be equal intervals, and here is going to be 10. And that one is going to be our final Regression Kriging. Now I would like to compare this model, that is the Regression Kriging of the generalized least squares plus the ordinary Kriging, with the deterministic model of the generalized additive models with 29 nuts. To do that comparison, we are going to use again this computer. First, let me see the 3D model of this one. Web, this one out. I want to see this one. Is this model? I want to take the data set. This one. Also, I want properties to use the clip. Apply, OK. And this one is the model. This model doesn't look really bad, right? It also has these bumps over here, but it's not as before, right? It is a little bit more discrete. Then the model is more realistic, right? And also, now I would like to put here the GAM, the Generalized Additive Model with 29K. But we can change here the color properties. I don't remember how to change the color. I believe we have to go to map here. No, add a new one. Solid color. Let's go to put a blue. Apply and OK. And then you can see the differences of these two models, right? But in order to compare the models, it's better to use a different tool, okay? Then I'm going to close this one. I'm going to take this one out, and I'm going to select this one also, the 29 here. And I'm going to go to plugins and look for profile. Profile tool. This one is a very good tool to compare. Oh, it has installed already. Then go to plugins and profile tool, terrain profile. With this tool, we can compare raster files, okay? Then select the raster file, then add a layer. And that one is going to be in red color. Then select the other one and add a layer and change the color for a blue color, for example. Then we have the red color that is going to be the regression kriging of the generalized least squares plus ordinary kriging, and with blue color the generalized additive model for 29 nuts. Then we can create here a section, for example from here to here, and now we can see the two models. From here to here. Double click to finish. Okay. And we can see the two models. As you can see, the two models are pretty similar, right? It is interesting, that one. Also, we can see a different section, for example, from here to here. Here, there are a little bit more differences, more significant differences, right? Here we have the elevation, and here we have the extension, right? And here there is an important gap, right? That is about 10 meters. Around 10 meters. Then we can see a different section, for example, from here to here. And that's the way that we can compare the two models. Also, we can see a section from here to here. But this section is pretty similar, right, for both. A section from here to here. Section from here to here. Section from here to here. At the end, if you asking me what is the best model, I don't have the answer for you, right? Because each of these models is provide you information, right? And that's the important thing. You want to extract information in order to take a decision, right? And it depends about your necessities, right? Sometimes maybe one model is better, or sometimes maybe the other model is better. The thing is that you have to play with the data in order to get the information that you need, right? And for example, if you have the GAM model and you have also information for previous year, because you were to the field, I don't know, 2 years ago, and you take the measurements of the groundwater also, and you have that measurement, maybe you can do another generalized additive model with that data and compare both models to see what is the differences or what are the similitudes, right? And you know, you can do a lot of things with the data. The goal is to get information to take decisions and to make sure that decisions are the good ones. Then as much information you have, better are going to be your decisions, right? Then you don't want to discard a model. Both models are good and both models are offering you different type of information, okay? Well, that's it for today. Thank you very much for watching this video and see you on the next lesson.